He's also the co-founder and scientific advisor to Mind Foundry. So in addition to his leadership activities, his research activities are similarly diverse. He's worked in a wide range of areas, really running the gamut from theory to also a real focus on real-world applications. He's been hovering around the AutoML space for at least 15 years or so, I would say. He's got a lot of visible work in this area, in AutoRL and AutoML in the past few years, but also around 15 years ago, he had some early work in Bayesian optimization. So yeah, I'm excited to hear his talk. And please join me in welcoming Stephen to the stage.
Thank you very much indeed. I hope everybody can hear and see me. It's an absolute pleasure to be here, especially because as Roman politely said, I've been hovering around the AutoML space for quite some time. In fact, I think I'm a little bit like a dog that goes round and round in circles before going to sleep, and I still haven't kind of settled yet. So what I'm going to talk about today in some ways is not AutoML. So, but I hope not too many of you will leave, because I think there's maybe some interesting things. Some of you will certainly know of these, but I hope that they will still be interesting. Let me move on. Most importantly, we all know, those of us who lead groups, that all the actual research is done by other people. And I just really want to say an enormous thanks to Sean, Elle, Lawrence, Diego, and John, and a bunch of other people on the periphery as well. But these people have really pushed our state of the art and our state of understanding forwards. I'm going to start out by talking a little bit about generalization. I'm aware this is not 1991, although I will have some slides that take us all the way back to the early 1990s, because in some ways, it kind of all goes back there. And some of the things that we obviously want generalization for is models that perform really well outside of a narrow set of training examples, be that in images, be it in signals, or whatever we may be doing. Generalization is one of those tricks to be able to try and find really good out-of-sample performance. The other thing that we would like is, although we're all in very much, we enjoy creating models that maybe do continuous meta-learning or continuous AutoML, we also would like models which persist for as long as possible through our data sets. That's not just good in terms of timing and the cost on our servers, but it's also just good practice in terms of the sheer scale of power that we're using to train up many of these very big models. And the final thing, which we often don't think about, is generalization has a really strong overlap with resilience of models to perturbations or adversarial attacks. So for those of you who are complaining of jet lag and have to fly back, do not go on a pig. It is not an airliner. And these kind of things really point out the fragility of many of the models, both shallow and deep. Remember, these kind of attacks work across an entire range of complexities of models, from fairly simple nested MLPs right the way up to vision transformers. So I'm going to kind of start by focusing in on why I'm particularly interested in generalization. I make a very proud statement. I'm a Bayesian, okay, and that often people kind of laugh, but I'm not such a hardcore Bayesian that some of my friends are not frequentists. But I have always really been annoyed by deep neural networks right from the get-go. When I sat and I spoke with Jeff Hinton and talking about these deep nets in vision, and then people like Andrew Zisserman, who said, look, you have to embrace this revolution. These models, they're kind of non-Bayesian, and we don't really understand why they do so well, but they're just so good compared with everything. And I'm like, but they're not Bayesian, they can't be good. And they're really, really good. And yet we know they're incredibly overcomplex. And as a Bayesian, I kind of go, well, we need to put a regularizer on there, at least something. We don't. And they just work, and it's like magic. So if we want to believe in magic, that's great. But I really want to understand how these things kind of can work, at least in my head, small though it may be. Okay, so let me kind of leap in back to 1990s. And I have a nice little slide where I picked this up later. I first came across this back in NeurIPS in 1991, where there were like 150 people and you could sit down and have coffee. NeurIPS never had such good cheese as the lunch here, by the way. I just want to say a shout out to whoever organized the catering. Thank you for the cheese. It's really good. So, and the Bayesian view, really opened my eyes. And this was sort of work that was done by folks like David Mackay, John Moody, and then kind of picked up in books like Chris Bishop's book, which is on over there on the left. And this kind of Bayesian view is that there is a sort of a natural contraction or a shrinkage or a compression of the probability distributions of our models over the space of data. And learning is all about shrinking the parameters that do something useful by learning from data. And that, of course, turns out to be pretty useful because not every parameter is going to help us actually model our data. So there is beginning to be a little bit of a link with things like AutoML. And of course, people like John Moody would use these ideas to do network pruning and a whole range of resource allocation problems. And this Bayesian view is something that from the 90s really has become popularized again by a nice paper that was published 2 years ago by Andrew Gordon Wilson and Pavel Ismailov from New York. And you can see what's happened is that the black and white pictures have become color, and that's the advance of the last 30 years. But this paper goes a lot further because it looks at modern machine learning from maybe a more historical traditional viewpoint. And that's we need to have models which can generalize well across data sets. And out on the left, they've got things to do with CFAR and MNIST and a whole bunch of things. And the two things which I'm going to highlight now that they say is we can represent large hypothesis spaces. Large hypothesis spaces mean we have big hyperparametric models which are incredibly flexible and they can do a lot. And if we're going to do that, we need to have some really funky ways to contract the massive probability distribution in that hypothesis space to stuff that's useful for my data. But I don't want to compress it too much, but I want to compress it enough so I learn and hopefully I transfer that learning to out of sample context. And the second thing that they point out, really, I guess really obviously, is that even if the hypothesis space constrains the truth, the best model, this sort of lottery ticket, if you like, is within my hypothesis space, I never have a guarantee that I compress learning from finite data to that model, but life gets a lot easier if I have things like inductive biases. So inductive biases are really, really cool because in many ways, choosing the right inductive bias reduces the space of configurations and really helps me in everything I do, whether I'm doing standard optimization or whether I'm doing some kind of on-the-fly AutoML. So I think these things are really very, very important. And of course, we're incredibly familiar with inductive biases, and I would argue things like classic Tikhonov regularization. So here we go back to the late 1970s, Tikhonov and Arsenin's work, and this is really just saying, all things being equal, science, the scientific principle of data fitting means that we should be trying to penalize models that have high degrees of curvature. And there's a whole bunch of reasons for that. Tikhonov wrote about these in terms of Radon-Nikodym derivatives and a whole bunch of stochastic calculus as well. But I'm just going to put that down there as saying we kind of have my drawing, because I've never worked out how to use proper drawing packages, so I'm afraid it's freehand. The red is a piece of metal, okay? And the blue are springs, and the black are my data points. And I have a piece of metal which has got a bending energy. The more I try and make it bend to meet my data, the more work I have to do. And if it's really stiff, I don't fit the data and I've got energy in my springs. So my goal is to minimize the total energy of the system. And what we end up with is regularized least squares. So if any statistician tells you that regularized least squares is really complex, it's just about bending a piece of metal through some springs and nails and things like that. And really, all we're doing in these situations is making sure that we end up with models with low curvature. Maybe we'll see a little later why that might be a good idea. And we try and fit naturally, we try and fit to the data as well. From a kind of formal Bayesian perspective, what that means is that this regularizer, we can turn the handle on all of this, and this kind of compression, these sort of bendings end up through a lot of lovely work that David Mackay did in the 1990s. What these end up being are log priors. So we put an inductive bias or a prior on our parameters in the model, and we look to see how much work we do moving those priors to posteriors in order to try and explain the data. So kind of very elegant. And we can do it in many other ways. We can do noise injection, and this again is something that Tikhonov spoke about in that paper in the late 1970s. Because we're really dumb, we wrote about it again in 2020, having kind of forgotten that it was, of course, all done in the late 1970s. But this diagram again is in color because it's modern, and what it kind of shows in a friendly way is as you inject noise in something like here, just a simple multi-layer neural network, as you successively inject noise, what you end up with is smoother and smoother or lower frequency outputs. And if you do Gaussian noise, then you have absolutely, it just looks like a ridge regression. And we're going to come back to this notion of noise injection a little bit later. So, and we can achieve all these things in a great many other ways. I saw some nice work out there on early stopping and cross-validation. I know there's people worrying about things like momentum, weight averaging, and learning rates as hyperparameters to try and do AutoML over the setting. We can do all that. Stochastic weight averaging, Bayesian model averaging, and a lot more. And I'm kind of holding sharpness for a little bit because that will be the focus of the big part 2 of this talk. But most importantly, and this is a paper that comes from, a figure comes from Keskar's paper. If we find equivalent local minima or equivalent energy solutions, we would favor ones that are somehow smoother or less sharp because they are more resilient to perturbations, and that means they're more likely to be valid and have good generalization error. A little bit more of that later. So the first part of this talk is about learning the dynamics. And I think I'll skip through this pretty quickly because actually the take-home message is you can do a load of really nice stuff, but the other take-home message is there are still some problems. So let me kind of point to a few things. I think I'll skip through a couple of these. Our goal is to try and learn something about dynamical systems. And again, I saw some really nice posters out there worrying a little bit about things like time series and a whole range of interesting practical problems. Dynamical systems crop up again and again and again, whether you're doing your flight control surface modeling in an aircraft or worrying about predator-prey models in ecology. Dynamical systems are really worth learning about. And probably the best way that we know right now, if we have access to it, is that if we can build up something like the Hamiltonian and use a physics-informed model, then we can solve many of these hitherto difficult problems in a really nice way, and we can roll things out. So rather than in the top diagram, and I'm wondering whether I can make this work if I go close enough here. Okay, so here will be a kind of classic way of doing things whereby we read in a couple of states of nature, and our goal is to try and estimate how these are going to vary in the future. In this case, they're derivative. And we could do this completely using just a standard model. But if we re-represent what we're doing, and again, representation is everything in this game, using a Hamiltonian, we can take auto differentials of that. And the nice thing is that we have conservation of energy, conservation of momentum. These are what we would call symplectic models. They obey the laws of physics, and I think that's really nice. Certainly when we were thinking about doing all these things and using things like neural architecture search, part of what we were trying to do is to say, let's search over reduced spaces which obey the configuration laws of the problem that we're trying to solve. And that's something that we don't always think about, that most problems have got constraints that we really need to bring in. Furthermore, learning those constraints is often a really good thing to be able to do. Again, I'm just going to skip over these a little bit. We don't even need to make these things energy conserving. We can allow them to be what are called port Hamiltonian models, whereby the limiting problem of having a conservation of energy can be reduced by having a much more expressive and much more general formulation. Let me go to say, and it works, you know, you kind of like ground truth. You've seen plots like this over many, many years, whereby things like port Hamiltonian models give incredibly good reconstruction of the future attractor or rollout of dynamical systems in comparison with sort of baseline models. Most importantly, we can transfer all these kind of things. So those sort of base learning models are really nothing other than a kind of neural ODE, which is sort of learning a reservoir or a basis of bits of solutions associated with particular problems that we give it with different boundary conditions. So we can build up a large training set of many different differential equations with many different boundary conditions, and we can have a single model which is learning to represent all of those. When we do that rather neatly, we can then say the final output that we get, we chop off the head of this model, we can show that that's nothing other than just a linear combination because we're dealing with homogeneous differential equations. And that means these, in effect, form eigen solutions. And we can just have linear operators doing all these. We can just do matrix to do inversion, or we can be a bit funkier and we can do some kind of fully Bayesian scheme. And what we end up with is models which work really well out of domain in different training areas. So I think this was the kind of big, you know, oh, that sounds absolutely great. And you run it 20 times. And of course, the linear final layer works really, really well. But then you begin to ask the question, where's the failure mode? So this all seems to work. What's the problem? The real problem is we still get incredibly bad solutions. Why do we get incredibly bad solutions? And we look back and it's nothing to do with all those kind of building up a reservoir of basis functions or anything like that. It's these bloody neural networks, you know. So having said they're great and they work, they can go wrong so badly. You know, why is this? And you kind of go in and you say, you know, it's always been a bit of a joke that you do kind of graduate student descent. You get your grad students to try many, many different batch sizes and learning rates. And they kind of go, ah, I found one that works. That's great, NeurIPS paper. So, and of course, this is feasible and we can automate this sort of search. It requires extensive hyperparameter tuning. And we still all worry a bit about hyperparameter tuning, and that's part of AutoML. I'm not convinced it should be. So kind of like, this is where people begin to throw old food at me and smelly cheese and things. I think it's just, I'm not convinced it's a problem we should be trying to solve in AutoML. I don't think hyperparameter tuning is worthy of the power of AutoML. The reason being is things like batch size and learning rates and all those things, we have a huge amount of theory behind what they should and could be. And I'm going to talk a little bit about that in part 2. But it still doesn't answer the question, what the hell's going on? So the next part is all about the dynamics of learning. And this kind of is half-baked, like the best baguettes in the morning. And I just really want to try and get to the bottom as to what's going on with these deep models. And the bigger they are, often the better they are, which just goes against everything I ever learned right the way back from the 1990s. And I want to introduce this diagram again that comes from one of the 1997 paper. The diagram I showed you before, which is Keskar's paper 2017 on large batch training. And this sort of idea that somehow sharpness, which is to do with the generalization gap between in and out of sample data, is something that we want to try and minimize along with trying to solve the problem. And what we know from random matrix theory, and you know, probably one of the best papers we ever wrote, which is Diego Granciol's, it appeared in JMLR, also is probably one of the most mathematical and impenetrable. You know, Diego was a proper mathematician, and I had to have 2 coffees before I gave him a supervision. Otherwise, I had no idea. Actually, I never really understood anything, but it seemed to work really well. And most importantly, he showed there are, of course, really, really strong theoretical reasons why learning rates and batch sizes should be related to one another, and how they are not just degrees of freedom we should be optimizing over. There is a kind of Pareto front for different problems, and so on. And you can trace all that back to all of these beautiful kind of Marchenko, Pasteur, and Gauss, Lanczos approximations of the spectra, the spectral norms of matrices, and a whole range of funky things. And of course, this isn't new. Jürgen Schmidhuber and Hochreiter, way back in the late 1990s, were also writing about flat minima, and there's been a lot of interesting work over the years. But none of it really in what I would call the era of big data and big models. And that's kind of what I want to talk a little bit more about. So before I do that, I want to introduce you to a couple of old friends here. Firstly is the Hessian. The Hessian matrix is much maligned. It's just a matrix of second-order derivatives of the loss with respect to the parameters within our model. But most importantly is that if we imagine it being positive definite, so kind of in a bowl of a solution, this guy looks like an inverse covariance. And what we know from that is that the eigenvalues of this Hessian, and this can be really big, this could be like a billion by a billion, this matrix. So they're pretty big matrices. The scales of this matrix are going to be related to the sharpness. So importantly, all you now need to know is if we have a large eigenvalue of the Hessian, then we have a small curve, as in a small scale associated with the loss in this direction. That means it's sharper. So big eigenvalues of the Hessian correspond to sharp directions. What should the eigenvalues of a matrix like the Hessian be? Well, amazingly, generalized Wishart matrices, which is what the Hessian is a member of, and their eigendensity is given by the Marchenko-Pasteur distribution. It looks like this. I've not put any zeros in there because it could be negative. These things are not guaranteed to be positive semi-definite. We could have saddles and a whole bunch of things, but the eigenvalues, so this is the probability distribution. So if we take that, what does it kind of look like in practice? The reality is it looks a little bit more like the left. So we got this continuous bulk. That continuous bulk is really the large-scale Marchenko-Pasteur distribution. This is what you get from random matrix theory. And this says this is what the eigendistribution or the sharpness distribution in all the different directions of the parameters of my massive deep network, this is what they look like. But the reality is that you have a bulk distribution, but you have a few naughty eigenvalues. And these occur even at initialization. And different initializations will have different numbers of eigenvalues, which kind of go, I'm antisocial. I don't want to be part of the bulk, and they're just really big eigenvalues. And they correspond to, out the gates, at the get-go, large sharpness directions within your problem space. And they may or may not be a bit of a problem. The reality is really close to this kind of model. Here's halfway through training a VGG16 deep net convolutional neural network on CFAR 100, and this is what the distribution of eigenvalues of the Hessian look like. You see the bulk, which is the Marchenko-Pasteur distribution, and you see these really naughty eigenvalues, which are kind of really big, and they correspond to big, sharp directions. Why is sharpness no good? Well, sharpness means even if my training solution is pretty good, small perturbations, the kind I expect from different batches or maybe from out of sample distribution, mean that it moves my loss an enormous amount. So I have extreme sensitivity to things that I can't control, and that's never a good thing in life. Okay. So we roll on a little bit, and around about 2021, I know this was work done in 2020, guys at Google wrote a very influential paper, which is called SAM, Sharpness Aware Minimization. And what they said is that you should be trying to pull in that worst case eigenvalue. So broadly speaking, we can think about the overall metric of sharpness and therefore a generalization error in terms of that largest eigenvalue. And what they did is develop an algorithm which goes through a whole bunch of steps, but most importantly, it just drags that largest eigenvalue in. They showed some impressive performance, and we would agree you can get impressive performance, but you can also get really awful, a lot worse performance. And again, that's counterintuitive. This is a really nice piece of work, don't get me wrong, but why does it work sometimes, not works the other time? So again, what's going on here? And we certainly wouldn't be the only people to talk about that. There are several people who've done these experiments and found. So importantly, out on the right-hand side, you can see out there in these plots how this is with the sharpness aware minimization, how those top eigenvalues are being dragged in on same problem, same initialization, and that helps with the generalization performance. So that's absolutely great. That's the kind of thing that we want. In effect, we're performing a regularization or auto pruning of our big model in order to try and improve the generalization. The next thing I want to introduce is what's called the edge of stability. And that edge of stability is just a classical framework which says that if I'm performing any kind of optimization, then the learning rate needs to be less than 2 divided by the maximum eigenvalue of my Hessian, unless I'm going to have an unstable solution. This is a lovely picture that comes from Cohen's paper in 2021, and that just shows that the edge of stability is 0.1. In this plot on the left, they set the learning rate to 0.09. On the plot here, they set it to 0.11. In this case, we have a stable configuration. In this case, we have unstable. So me, 20 years ago, would go, you need to reduce the learning rate below the edge of stability. But actually, it turns out that's probably the worst idea you could ever do. So instability is truly all you need in life, as so many things. So that first phase of learning is that with the learning rate, we end up with this sort of gradient flow or progressive sharpening, whereby everything is stable and our solutions are crystallizing or cooling to solutions whereby those top eigenvalues are actually pulling away from the bulk and getting even bigger. So we're getting more and more sharp solutions. That's absolutely not what we want. And I think the really interesting thing then is we suddenly hit the edge of stability, and the different eigenvalues do this individually. So the first one, the worst one at initialization, gets bigger and bigger and bigger, and then hits the edge of stability, and we start getting a really big oscillation in the parameters within the model. And progressive sharpening stops, and then something seems to happen. We have a really big oscillation, everything drops back, and then other eigenvalues begin to follow it, kind of going, oh, that looks like a good game. I want some of that. And they start peeling away. I'm not showing them, but really interestingly, the moment you start getting this, when you look at the eigenvector, which is a parameter vector, you then take that and you calculate the output from the model. These are like pieces of a solution. If you're doing regression, they're little bits of a curve. If you're doing classification, they're bits of decision boundaries. And they're reasonably local, which is really interesting. So what we're doing is we're kind of building up a complex solution in terms of eigensolutions, compounding them throughout training. But this goes on and on and on and on, and we get these kind of oscillations. The nice thing about these instabilities is when we begin to look at the validation loss, and I think this is one of the, down here, one of the key plots, is here is the instability where the maximum eigenvalue goes above the edge of stability. And as we begin to approach that, the validation loss through the instability drops really significantly, and we just see it again and again and again. So we begin to get instabilities are driving reductions in validation loss, and they drive training loss as well. So accuracy is something that is deeply embedded within the notion of instabilities within the models. So these oscillations in the parameters occur in the directions of maximum sharpness. Okay, so we don't want really sharp directions. So if I said this is the direction of maximum sharpness, we really want to regularize this, it's too sharp. There are many things that we could do, one of which is we inject noise. And these oscillations, here is a TS&E plot of what's going on. And this is a projection from a VGG16 model. And we can see the parameters as we hit these instabilities, in effect, are just almost going through like a Gaussian noise injection. We're actually regularizing, but critically, we're only regularizing in the directions of maximum sharpness. And that is a really good thing. And we can show that passing through these instabilities. What we end up with are these sort of, we kick off. The dashed line is where we start, and the solid line is the end point. And we end up kind of going over the edge of stability, that's down here. We start getting some really funky instabilities. And as we exit these instabilities, this is the second derivative of that. This is the maximum eigenvalue. You can see we end up with a much broader spatial region in this slice through the parameter space where we have low sharpness, which is all below the edge of stability. So these instabilities, by injecting oscillations preferentially in some directions and not others, are actually driving our system to form far more generalizable basins and losses. So that is a really good thing. How is this oscillation taking place? Well, it turns out the Hessian is kind of entering these unstable regimes, and it's kind of spinning, it's just oscillating, it's not really contracting, it's not doing anything in terms of its spectral radius, but what it's doing is it's rapidly changing its orientations. So when we begin to look at what's happening with the parameters or the weights, we see these oscillations taking place in directions of maximum sharpness. So we have these pretty sick oscillating Hessians, and as we go through a progressive sharpening and instability, we end up coming out with a flatter solution, which we would expect from something that looks like noise injection. So here was the aha moment. Deep neural networks with nothing else in them whatsoever are always self-regularizing so long as we have instabilities. That means that we really want to make sure that our learning, the temperature of learning, and that's defined by the learning rate divided by batch size, that is large so that we promote as much instability as we possibly can. So here was this kind of crazy thought, which mirrored many papers we've been reading, which say you get really good results by having learning rates of 5 or 10 when everybody else is using 0.01. You need these instabilities. So we started looking at these learning rates. These are learning rates on the bottom, and these are on a log scale. So here is a learning rate of 1 here, and learning rate of 2, 3, 4, 5, etc. This is on with an MLP. It's got 5 hidden units on MNIST, and this is the VGG16 model on a CFAR 5K. I think this is even sweeter, but I kind of put this in to show the results hold across models with many different degrees of freedom. But most importantly, this is this edge of stability. As we increase the learning rate, we don't really see much of an improvement in the test accuracy, which is shown on the y-axis here. Bigger is better. And again, also with the fashion MNIST, we don't see very much. So we've got virtually no change as we begin to change the learning rate, a little bit of a gradient, but we really begin to see dividends if we make that learning rate larger than the edge of stability, and we can make that learning rate within reason crazy high compared with what we would normally have done. So very, very large learning rates would appear to be an incredibly important and very, very useful framework for solving many of these problems. So let's revisit some of this sharpness. This is this plot that comes from the SAM paper, and that's out there on this side here, showing how the top eigenvalue is being drawn in. We don't want to tame and pull in that top eigenvalue. What we want to do is actually, we just don't want to have an eigenspectrum with a bulk distribution and many, many, many eigenvalues which sit at large values. That means that we have an extremely high number of effective degrees of freedom within our model, and we potentially have an overcomplex solution. So what we'd like to do is to allow those top eigenvalues to do their instabilities, because we know that that improves the training process and gives us this noise injection regularization. But what we don't want to do is just penalize the largest eigenvalues. So here we take a little bit of a trip back to history, and this is back to 1991, which is such a lovely poster here. This is the poster from the Denver Conference Center showing NeurIPS. I never, even back in the day, I never really worked out what that was. It seems to be some horses and some animals which have nothing to do with NeurIPS, but it looks really nice. And then we all went up to Vail to go skiing, which, you know, is fantastic to have workshops where you can go skiing as well. So this is where I first came across, sat down with John Moody and spoke about the effective number of parameters. And he was talking about this really interesting result that comes from 1970 and Akaiki's work. And this for, oh dear, I do beg your pardon. Let me try. Right, no, get out of that. Can I go back? Yes, I can. So this picture, this equation in the middle says really rather nicely, the test error is going to be given by the training error for a linear system, plus a term that depends on the ratio of the number of parameters in the model divided by the number of training data points. And that comes out really nicely. And what John Moody did is say, aha, let's take where that comes from and I'll rewrite it. Of course, we're still trying to do this today. What we want is good test set, out of sample error. And we can relate that to the training error through what John Moody called the effective number of parameters. And it's not the total number. And that effective number of parameters, if we take this little equation down here, the kappas, he used a different notation. The kappas are the eigenvalues of the Hessian. Lambda is think of as a kind of regularization parameter, but it's a number and it kind of should sit at the edge of the bulk. So really what this equation is doing is telling us about the number of effective eigenvalues that sit outside of the bulk of the Marchenko-Pasteur distribution. We didn't really know that then. John Moody called it the generalized prediction error, and it's pretty darned good. It got picked up by people like David Mackay in his wonderful thesis in 1991 as well, with John Hopfield. And when you look at the relationship between the effective number of parameters and validation loss for many different problems, you find that there's really strong relationships. Don't worry too much about what this thing's saying. It's just a slight modification to make one of the terms invariant so that this regularization parameter scales on the same dimensions as the eigenvalues. But that's not really an innovation. It's just a scaling. And what we find is that these terms scale really, really well and correlate really well with out of sample validation error. And that occurs no matter what we're doing in terms of the learning rate, whether we've got smooth functions, in other words, very small learning rates with no instabilities, whether we have learning rates and batch sizes that promote intermediate levels of instability or even high instability. So we had the idea, well, hey, well, maybe we could use this in terms of some kind of generalization or regularization term to try and help models promote good eigen spectra, which we know lead to good out-of-sample generalization. And to help us do that, we kind of note that you can write those ratios of eigenvalues so long as the eigenvalues on the bottom are coming from a diagonal matrix, you can rewrite them just as the trace of a diagonal preconditioning matrix multiplying through by the Hessian. We were kind of excited by that, but also slightly disappointed because we've seen this equation in everything for about the last 40 years. So this is just over relaxation, regularization, and is the kind of thing that you find in a great many optimization books. Interestingly, though, if you make this preconditioner, which in here is G, if you make that a smoothed version and diagonal smooth version of the Hessian itself, you recapture all of Moody and McKay's work on effective number parameters that we know does the right thing and relates to out-of-sample validation. And that means that we actually now have a really strong prior on what G should be. And we can recover SAM and various other things as special cases. So this is what a couple of people, Diego Granciol and John Williams, been doing and come up with a couple of algorithms that work, that do that. And I should also point out, it's a popular topic. There's other people who are doing this from a stochastic systems perspective as well. But all things being equal, does it work? Yeah, it works pretty darn well. It works really well, even on noisy, no augmentation data sets. It works well on everything from CFAR. We've tested it on some of the vision transformer work. We've transferred it across to NLP and looked at kind of Hugging Face BERT data sets and so on. And we're yet to find cases where it doesn't perform as well as state of the art. It's virtually no cost because that preconditioning is diagonal and it's pretty cheap to evaluate. We can do, using Gauss-Newton and then the sort of Krylov-Lantsov iteration, we can do things really well. So I kind of point out, and I'm going to end in just a second, this is a little bit work in progress, but I think it's really very interesting because we spend so much time worrying about things like batch sizes, momentum terms, and learning rates. And I think that what I have now learned from all this is these actually are not necessarily big things that we should be worrying about. Topologies of model, much, much more. Though I will say right at the end my thoughts on kind of model topologies. This is a nice bit of work by Sanka and all that was done a few years back. And what they looked at without doing optimization was just looking at the eigenspectrum through the layers of a series of modern deep networks. And what they find is the eigenspectrum is really rather different across different layers. And they go on to show how you get smooth or oscillation behavior in the eigenvalues through the different layers, which lends itself potentially to future research, which does layer by layer optimization using some of these techniques. And wouldn't that be lovely? Because that really reduces the search space even more. So I'm going to conclude. Everything is difficult. Inductive biases can be really good, but the weak bit was always the sort of deep net side of things. Strong inductive bias in deep neural networks, especially things like physics-informed models and some variants of graph neural networks, constrain the hypothesis space so that without caution, what we end up with are learning models that never oscillate. And oscillations and instability really is all you need in order to get these self-regularizing effects. And we know that that leads to really good out-of-sample generalization. We don't need to learn learning rates. Above a certain threshold, these models work pretty well the same no matter what the learning rate is. But critically, we just need to make sure that learning rate and batch size is above the critical level to ensure that we have these unstable dynamics. And that cuts out an enormous amount of costly hyperparameter tuning. So my thoughts about big models are a little bit kind of up in the air. What I thought AutoML was going to lead towards would be piecewise construction and search over model configurations. And I still think it has a really important place in that space, possibly choosing inductive biases, possibly choosing various topologies of layers, but mainly in the context of ensuring that on a layer by layer basis, we end up with these extreme instabilities because they are what leads to really good performance, not necessarily the topology. Everything fits together, and we don't often consider any of these things. AutoML and neural architecture search, again, I think have got a really important place to play in modern science, but I'm not convinced that we can't do equally well by just having a really, really big network. And I think, just this week, we've started getting some results from some of the biggest models that we've looked at, kind of T5 backbone transformer models, and we see exactly these same phenomena, even in super large, ultra large generative models as well. So I think there's a lot of research that needs doing. I will end there. I've always liked this quote: civilization progresses by increasing the number of things we can do without thinking about them. And certainly AutoML is helping us do that. Thank you all very much indeed.